What I want to talk about today, and for the rest of our precious time together, is unsolvable problems or uncomputable problems, which are not the halting problem. So last time we talked about, the halting problem, and it says given any Turing machine M, come on now, and a string x, can you tell if M halts on x? Does M halt on x? I mean, when you run M with x as the input, does it halt or not? This question cannot be answered by any Turing machine. That means there is no algorithm. You cannot write a computer program which in general will be able to answer this question. All right. There are simple variations on this which are also undecidable. So I'm going to say this is uncomputable by a Turing machine. No algorithm can in general decide the answer. You might have specific examples which are easy enough to look at and just tell if it's going to halt or not. But there is no general purpose procedure which will always work for all examples. All right, and then yeah, there are some simple variations. So the same kind of question, but if you ask, does M accept X? This also is uncomputable. I mean, the difference between halting and accepting, halting could be accept or reject, right? But you can say very similar things to what I said last time, and you can show that this is also uncomputable. My goal for today is to describe to you two much more down-to-earth examples of more or less ordinary-looking things which are also uncomputable by any Turing machine. These which I just mentioned, they don't really qualify as ordinary-looking because they themselves are questions about Turing machines. But I want to give you something that you can bring home to your moms over the summer or something when they ask you, what did you learn about in that expensive college of yours? You can say, I learned some mathematical questions which cannot be answered by any computer. That's what I want to talk about today, which you could explain to anybody. They're not things that involve consider any Turing machine or whatever. None of that. Okay, so the first one is, the first one you could explain to anybody, although some people aren't going to like it because it's kind of super mathy. The second one is much more ordinary looking. But the first one is, I will say, another unsolvable problem. And I'm going to make no effort to explain to you why you should believe that this is unsolvable. You'll just have to take my word for it because it's very complicated, the proof of this, and I'm not going to get into it. But anyway, another unsolvable problem. This, though, is definitely like an ordinary-looking math problem. It says, given any multivariable polynomial in several variables. I said that. I meant with, I already said multivariable polynomial with integer coefficients. So the coefficients are whole numbers. No weird coefficients. So I mean something like, 3x squared plus 2x. This is a polynomial, right? But it's multivariable. So it could have terms in it that look like 4xy plus y to the 7 equals, I don't know, 8 minus 7x squared y. This is an example of a multivariable polynomial. This has two variables with integer coefficients, all right? The question is, can you find any integer solutions? That is, just a choice of numbers, x and y, which make this polynomial true. Now, I just wrote this at random. I have no idea if there are solutions in integers, right? I could use some fancy real analysis to find real number solutions to this by doing things like Newton's method, or like if you know some numerical analysis. It's definitely possible to find real number solutions, or perhaps there are no solutions, but you can prove that either way. But if you are looking for solutions which have to be whole numbers, this question is undecidable by any algorithm. So no Turing machine can do this computation. I don't mean this particular example. I just made that up at random. Maybe there's some kind of trick which would work in that particular example, but I mean, there is no algorithm which in general can take a polynomial like this and tell you if it has integer solutions or not. No Turing machine can do this. This was a famous problem for a long time, and this was actually one of the first problems which people had tried to solve for like hundreds of years. And then somebody ended up solving it by proving actually that there is no solution, that it's impossible to answer this question. So this was this is referred to as the Diophantine equation problem. It's named after one of the Greeks, Diophantus, who was one of the first people to consider something like this problem, and like a long time ago. And in the, I don't know if you've ever heard of this guy, Hilbert is a big figure in the history of mathematics in the 20th century. Around the first couple of years, 1900 maybe, there was a big conference of all the leading mathematicians in Europe, and Hilbert was like the keynote speaker at this conference, and he proposed a list of, I believe, 20 problems for the new century. And he said that, you know, this century is going to be marked by extreme mathematical progress, and he said, here's this list of like the superstar unsolved problems in mathematics of his day. And this was one of them. This is Hilbert's 10th problem. And for many years, you know, you could become a rich and famous mathematician if you solved one of Hilbert's problems. This was the 10th one. And Hilbert had no way of knowing this at the time, but it was eventually proved that there is no solution. And this wasn't shown until, so this was shown to be unsolvable in 1970 is when the proof was finally finished. So this was a major work. This is why we're not going to go over the proof. And actually, like, the proof is totally, it's way too hardcore, like, for me to, I can't read this proof. I would have to spend many months of learning all kinds of stuff, background to read this proof. So, but this was a big deal at the time, you know, to show that one of Hilbert's problems actually has no solution was not expected for this problem by anybody way back in the day. All right. So this is one that you could explain this problem to your friends if they know something about polynomials. I think it's not a horribly difficult problem to explain to people. The one that I want to talk in more detail about is actually very easy to explain to anybody, and this is called. This one I actually do want to talk about why you should believe that it's unsolvable, although we might not get to that until next time. This is a famous problem. It's called the post-correspondence problem. The post-correspondence problem. It's named after this. This is a person's name. Emil Post. One fun fact about Post: he did this like in the 40s, I think, 1940s. He came up with this, 30s or 40s maybe, around that time. Post is the person who invented the word string in computer science. Like, they use the word string to refer to strings. Little computer science trivia for you. I've always been no shade to Post. I've always been kind of dissatisfied with the word string. I'm still not quite sure why they're called strings. I don't know. Anybody have an opinion about that? They're kind of long and skinny, maybe? I don't know. They're not floppy, though. They have ends. I don't know. It's dissatisfying to me. But anyway, the post-correspondence problem. So Post is sort of like a second-generation theory of computation mathematician. You know, he wasn't Turing. He was like the next generation of people who learned from Turing and tried to go further with stuff. And Post saw Turing's proof that the halting problem is uncomputable, and he wanted to make a more sort of down-to-earth thing that was also undecidable by any algorithm, but something so innocent looking that you could even like explain it to a child. And this is exactly of that type. So it's kind of like a cute little puzzle, which seems cute. It seems totally ordinary, but it turns out no computer can solve it. And here it is. You're given some blocks. I'll call them tiles, like this. And they have things written on them. I'm gonna do just a specific example. They have strings written across the top and also across the bottom. This is how the post-correspondence problem works. And let's say 4 of them, although you could use as many as you like in a puzzle like this. You could actually make this out of paper or something. Give it to a kid. Although there's one thing that the paper is a little unsatisfying about. But anyway, these are the tiles. You also designate one of them to be the starting tile. So let's say I'm going to choose the second one, and this is how this is indicated sometimes. The starting tile is the one with the fancy border there. I did strings of zeros and ones, but they could be any strings you like. On the top, it's just there's a string going across the top and a string going across the bottom. And your goal, so this is sort of the puzzle as it is presented to you, and your goal is to find, so a solution is a choice of ordering of the tiles. You take these things and shuffle them around somehow. Ordering of the tiles. And repeats are allowed. This is what might be difficult to do with a kid on paper. You are allowed to reuse the tiles as often as you want. So maybe if you're doing this with your kids, you guys have kids, right? If you're doing it with your kids, then make 10 copies of each tile or something. Repeats allowed. A solution is a choice of ordering of the tiles with repeats allowed. You got to start with the starting tile. Starting with the starting tile, but you can repeat that one later on if you want to. But just the first one you use has to be the starting tile. Such that, here's what you're aiming for when you're, Such that, what you're looking for when you rearrange the tiles is you lay them all out in order, and the big string that you read across the top, you read across the top of all the tiles, the big string across the top has to equal the big string across the bottom. If that's true, then you've solved it. Or perhaps you somehow decide that it's impossible for this collection of tiles. All right. So such that the string read all the way across the top equals the string across the bottom. Sorry. All right. So your goal as the kid trying to do the puzzle is either line them up so that they have that property, or figure out somehow that it's impossible to do that. All right. Let's see if we can do it for this particular example. Now, I said this is an uncomputable problem. You'll have to take my word for it for now, but we're going to explain why. What I mean by that is there is no algorithm which can, in general, find solutions to this. Although it may be in this particular example, this is somehow an easy one, and we could figure this example out. And in fact, I made this one so that we could figure it out. Let's see. I'm going to do this. I've practiced this before. We'll see if it works. Come on. Yeah. Oh, yeah. All right. Did you do those evaluations yet? Mention that. If not, I'm impressed with that. Okay, can we do this one? Well, all right. We gotta try. So we have to start with the starting one, right? 1 0 1 0 1 1 0. Okay. What next? Anybody feel like you have an idea here? The basic strategy when you're trying to just mess around with this is, remember, in the solution, when I read all the way across the top, it has to be the same as when I read all the way across the bottom. That means in this second tile, the string on the bottom, I think you can say, maybe not exactly what it is, but you have some idea about what it is. Yeah. The first one? Oh, yes. Yeah, why'd you choose the first one?
Then it'll be 10101. So it'll be the same as the top one and the first one. And then we'll just add a 0 at the end.
Yeah. So the idea is, if you look at what we started with, on top, it begins with 101, right? That means on the bottom, it must also begin with 101, which means the next thing that I put there, on the bottom, I want it to start with a 1, all right? So that immediately rules out it's not that and it's not that. Now, it is possible that you could reuse the starting tile, although I kind of feel like that's going to really screw up the string on the top, right? So maybe we'll try the very first tile that's written there. Get rid of these. So I'm going to do this one, which has a 101 on the bottom and a 0 on top. All right? And then?
The last one.
Yeah, and I think now we can finish off with the last one. And this, I think that will do it, actually. Now the top string says 1010101, and the bottom string says 1010101. All right? So we did it. Hooray. All right? This is the post-correspondence problem. All right? So you did something that no computer can do. Isn't that awesome? No, you didn't actually. What no computer can do is no computer can, in general, solve any such problem. I don't know if you have an intuition about this. Anyone want to suggest? Here's a computer algorithm that can solve this problem. Can't you just try all possible orderings, right? This, what I wrote was just one ordering. Can't you just, with the computer, write down all possible orderings? Yeah. Yeah, this is the major problem. You are allowed to repeat the tiles, and so there is no brute force algorithm that can just check every possible ordering of the tiles because you are allowed to repeat. Like I said, I said as some kind of intuitive notion, I don't want to use this one right here because I feel like that would mess up the top. But maybe if you mess the top up like 20 times, that will somehow magically make it so that the bottom will come around eventually. I think in this example, actually, I would almost say for sure I should never use this one here because it makes 5 consecutive zeros on the bottom that would at some point have to be matched by 5 consecutive zeros at the top. But actually that is true. That is possible by using this one 5 times. So all of these things are, more complicated than it might seem. I'm just going to make some more insane-looking marks on here. This one here, that one there. So no algorithm can solve the post-correspondence problem. You could make a cute little, you could make this into like an iPhone game or something where you drag the little things here. People would not realize that they're trying to compute an uncomputable puzzle. I mean, it's not. There's nothing about it which immediately seems like it's going to be uncomputable. Let me just give you a little intro to the punchline. So we don't have enough time to do this now, so I think we'll cut it off at this point. But next time, it turns out that any PCP problem can be converted into a does the Turing machine accept or not problem. And this is how Post was able to show that the PCP is unsolvable by any algorithm. Because you can show that if you had a solver for the PCP, then this solver could be converted into something which tells you whether or not a Turing machine halts, and that is impossible to do. So I think we will leave it at that for now. Next time we'll discuss the procedure. It involves taking a Turing machine. I'll draw a Turing machine for you. You can break down all the arrows and all the states, turn that into a bunch of blocks, and then the solving the PCP is equivalent to solving the problem on the Turing machine. It's cute. We'll do it next time. All right. Have a good weekend. No. Yeah, the final exam will be in person. Be here. See ya.